What's up, everybody? Here are the solutions for the function section of the final review. So for the function section, basically what we are looking at is a few sketching problems, right? So for problem 1, we are asked to sketch the graphs of some elementary functions, and in part A we are looking at the functions x squared. Let me just rearrange the screen a little bit so I could see this a bit better. I'm looking at the problems on my own screen here. X cubed, x to the fourth, and so on. Basically, we're looking at the function x to the n for n even or odd. And to sketch these graphs, let's start with y equals x. So for that particular one, we know that's just a line going at 45 degrees. And that's what it looks like, right? Nothing too complicated about that. What about y equals x squared now? Well, that one I know is going to be a parabola opening down, looking just like so. Then to sketch the graph of x cubed, that's going to look like that, except it crosses the axes, right? So instead of having the parabolic shape that x squared has, it crosses on the other side when x is negative. However, if I do y equals x to the fourth, it resembles the shape of x squared, right? The only difference is x squared is a bit wider because it increases slower, right? So in general, when I have an even, the graph of the function x to the n is going to resemble the parabola, whereas when n is odd, the graph of x to the n is going to resemble x cubed, right? The x cubed function, so it is going to cross the axes just like so. So that's the first part. Right, now let's look at part 2, and for part 2, or for part B rather, so I'm looking now at 1b. Basically what we have is, I'm looking at reciprocals of functions, right? So I'm looking at 1 over x squared, 1 over x cubed, 1 over x to the fourth, and so on, 1 over x to the n when n is even and or odd. Okay, so let's take a look at what these graphs look like now, and I'll draw 1 over x first. Basically what that's going to be is, it's this shape, right? And we have horizontal and vertical asymptotes just like so. So this is y equals 1 over x. But if I move on to graphing x squared, it's going to look a little bit different. It is no longer going to cross, it's no longer going to be in the third quadrant here for x negative. In fact, it's going to look like this. Well, I'm sorry, 1 over x squared, just like so. Okay? And now if I move on to 1 over x cubed, again, that's going to look more like the 1 over x function, whereas if I draw 1 over x to the fourth, it's going to look more like 1 over x squared. Right, so they're going to be very similar. The only thing is the rate at which they approach their asymptotes, right? So then in general, when n is even, the function 1 over x to the n is going to resemble the x squared graph, right, the 1 over x squared graph that we have up here, whereas if n is odd, the function is going to resemble the graph of 1 over x, something like this. Okay, so that's the solution for 1b. Now let's take a look at problem 1c, where we are graphing nth roots now. So for 1c, what we're looking at is the following functions. We're looking at square root of x, cube root of x, fourth root of x, fifth root of x, and so on. Okay, we're looking at the nth root of x for n even or odd. So first I'll start with the square root function. That one is fairly easy to draw. It looks like this, right? And the way you want to imagine this, it's a parabola that's on its side, except we are not interested in the negative part. We're only interested in the positive part. So this is what the square root of x function looks like. Now if I draw the cubic root of x, it's going to look fairly similar, except I cannot take square root of negative numbers, but I am allowed to take a cubic root of negative numbers. So the domain extends and the graph looks like that for the cubic root. What about the fourth root? The fourth root is going to behave more like the square root in the sense that I cannot take a fourth root of a negative number, so the domain is only from 0 to infinity. But a fifth root is going to behave again more like a cubic root, right? So notice how the shapes are similar over here for these two. So in general, when n is even, the graph of the nth root function is going to resemble the square root, whereas if n is odd, the graph is going to resemble the cubic root. So for the positive part, it looks a lot like the square root, but for the negative part, we can extend the domain in this way. Okay, so this would be the solution for 1c. Now let's take a look at 1d, which has us graph trigonometric functions. Let's see, I'll start with y equals sine of x, and I'll only graph it from between 0 and 2 pi. Maybe I'll start at minus pi, because we'll need that later. So this is minus pi, that's 0, this is pi, and this is 2 pi. And I know that the sine graph is going to basically look like that. This is sine of x. Okay, let's go ahead and also graph cosine. So we'll put that up here, and cosine is very similar to the sine graph, except that it's shifted horizontally, right? So this is pi, let's say this is 2 pi, this is minus pi. It starts out like that. It has a 0 at pi over 2, then it goes down to all the way to minus 1 at pi. It has a 0 again at 3 pi over 2, then it goes all the way up to 1 again, just like that. And then of course I have the mirror image down here. So this is at minus pi over 2, where I have these roots. Okay, so that's the graph of cosine of x. And using these two, if you know these two, you can pretty much get all of the other trigonometric functions. So I'll start with tangent of x. I'll do that down here. And I know that tangent of x is sine of x over cosine of x, which means I'm going to have vertical asymptotes everywhere this denominator is 0, everywhere cosine of x is 0. So I'm going to have vertical asymptotes at pi over 2 and minus pi over 2. Okay. What is tangent of 0? Well, sine on top is going to be 0, so tangent of 0 is 0. And notice, as I approach pi over 2 from the negative side, the top stays positive, right? That approaches 1, and I'm dividing by 0 here, so I approach plus infinity. And I'm dividing by 0 from the positive side, okay? As I'm approaching pi over 2 from the positive side. So this shoots off to plus infinity like that. And then on the other end, as I approach pi over 2 from the negative side, the sine part is going to be negative. We're down here, so the numerator is negative. But the cosine approaches 0 also still from the positive side. So then I actually shoot off, because of that negative, to minus infinity. So that's the graph of tangent. And of course it's periodic, so it repeats itself like that, right? So I have many copies of that shape. So that's tangent of x. That's this one. Now, knowing I can do the same trick, right? Knowing this, I can do the same trick for cotangent, which is cosine of x over sine of x. And because the sine of x now is in the denominator, that means that my asymptotes are going to be at 0, pi, 2 pi, everywhere the sine part is 0, okay? So this is pi, this is 2 pi, etc. And this is minus pi. Okay, so how do I draw this now? I can either think of this as 1 over tangent. So if I take, this is pi over 2, and in fact it's easier to do it as 1 over tangent. As I approach 0 from the positive side, I'm dividing by a positive 0, so I shoot off to plus infinity here. As I approach pi over 2 from the positive side, I'm dividing by infinity, right? It's 1 over infinity, so I hit a 0 here. And as I pass pi over 2, my sign changes, right? I'm dividing by minus infinity here. So I switch on the negative side, but then I approach 0 again at pi on the graph of tangent. So I divide by 0, right, because it's 1 over tangent. This is the graph of cotangent. And of course it's periodic, meaning it just repeats, just like the sine and cosine graph do. Okay? So notice that the zeros of the tangent graph become the asymptotes of the cotangent graph, and vice versa, right? The asymptotes of the tangent graph become the zeros of the cotangent graph. Okay, so I know that. How about secant and cosecant? Right, this should be a little bit easier because it's just 1 over sine and 1 over cosine. So let's go ahead and I'll start with cosecant x first. That's 1 over sine of x. And again, sine is in the denominator, so that means I'm going to have asymptotes at every multiple of pi. I'm going to have vertical asymptotes because I'll be dividing by 0. And now I just plug in. So I look at the graph of sine up here. Of course, as I approach 0 from the positive side, I'm dividing by 0, so I shoot off to plus infinity, just like that. Now sine of pi over 2 is 1. Cosecant of pi over 2, that means it's 1 over 1, so that's also 1 here. And as I approach pi from the positive side, again I shoot off to plus infinity, like that. If I put all of this together, this is what the cosecant graph will look like. Ones.
If you work it out, it turns out it's going to look like this.
Well, it's going to shoot off to the asymptotes like that. And then it would repeat itself, right? So you have one positive, one negative, one positive, just like that. These little U shapes. Secant is going to be very similar. Secant is 1 over cosine. Which means now my zeros are at the, not zeros, my asymptotes are at the zeros of the cosine graph. So that happens at pi over 2. At pi I don't have that, but I have another asymptote at 3 pi over 2, so let's go ahead and draw those in. Minus pi over 2, etc. Okay? And you can either think of this as, okay, just shift the sine graph to obtain cosine, which means I shift the cosecant graph to obtain secant, and that's very easy then, right? That means I'm up at 1 here, looking like this. Oh, that wasn't the prettiest curve, but you get the point. And I'm down at negative 1 here, looking like this. And then it just repeats itself, like so. Okay? So that's the graph of secant x. And that finishes off part D. So now let's move on to part E, which has this graph inverse trig functions. Let's see how we do that. So for problem 1E, let's start first with y equals arctangent of x. Okay? So I saw that the graph of tangent, at least between pi over 2 and minus pi over 2, looked like that, right? And it leveled off to the asymptotes. To obtain the graph of the inverse function, all I have to do is reflect this about the line y equals x. Okay? So when I do that, what I obtain is the following graph. I'm going to have now the vertical asymptotes are going to become horizontal asymptotes at pi over 2 and minus pi over 2. And on one end, the function is going to level off like that. On the other end, it's going to level off just like so. So this would be the graph arctangent of x. We're going to do the same trick with sine of x, with arcsine and arccosine. So let's go ahead and do it. Y equals arcsine of x. Well, I start with the graph of sine, and let's go ahead and graph it between 0 and pi, and then let's actually go all the way to minus pi. Okay, so that's what the sine of x graph looks like between negative pi and pi, and I'm going to try to reflect that about the y-axis. Not about y equals x, the 45-degree line. So what I obtain is the following picture. I'm up at pi here, I'm down at minus pi here, right? So these points get reflected over there. So from here it goes to plus pi, just like so. The max of 1, the axes
switch roles here. the function that I'm looking at is this, right? However, in order for it to actually be a function, I need to cut it off right over here. Okay? So it's defined only between -1 and 1. Okay? So another way to visualize this is, instead of drawing the sine function like this on the x-axis, you draw it on the y-axis like that. Okay? And for it to be a function, then you're only interested in that piece right over there. Okay, so that it passes the vertical line test. So that's how you can think about these reflections over here. Let's go ahead and also do arc cosine real quick. So I have y equals arc cosine of x. Of course, I'm going to start with the graph of cosine. And I know that that one, I'll draw it between 0 and pi. Looks like that. So I go ahead now and I reflect it, right? And of course, I'm not going to think about this as a reflection. I'm simply going to think about this as just draw it out on the axes. Okay? So I start like this, I hit my 0, I finish off like that. There's the graph of arc cosine of x. So that's that part of the problem. And lastly, for problem 1f, what we have is we're looking at now y equals e to the x, which is simple to draw. Basically, the graph of e to the x has a y-intercept at 1 always, because e to the 0 equals 1, and it levels off as x goes to minus infinity like that, right? So this would be the graph y equals e to the x, and the limit as x goes to minus infinity is 0, just like so. And now, of course, I'm going to draw its inverse function, y equals ln x, and the log now has, the y-intercept is going to become the x-intercept at 1, and we have the vertical asymptote now, so the function looks like that. Okay, so those are the graphs of e to the x and natural log of x. So that finishes off problem 1, and now we do a few more curve sketching problems. So let's take a look at problem 2 now. And I'll start with, of course, I'll start with problem 2a, which has this graph two curves. The first one is y equals 3 times x plus 1 quantity squared minus 1. And of course, what this is going to be is a parabola shifted to the right, to the left, 1 unit. And this is now shifting it down 1 unit. So when I graph that, starting with the graph of the original y equals x squared, what I end up with is I shift to the right, to the left 1 unit, and I shift down 1 unit, so I'm now down over here. Okay, so this would be y equals x squared with those corresponding shifts, but because I have a coefficient of 3, what that's basically going to look like is it's just going to be a little bit narrower, right? Or you can think of it as a vertical stretch. So that's the curve in question. Not the best drawing, but again, we're just looking at sketches here. The second curve that we have to sketch
is y equals negative quantity 2x plus 1 cubed plus 1, okay, which I'm going to rewrite as negative 2 cubed. So I'll factor out a 2 from the parenthesis, and I'm left with x plus a half cubed plus 1. So now I have a left shift of 1/2, and I have an up shift of 1 unit. Okay? And then this 2 cubed, all that does is it makes it a little bit narrower. But notice now I also have a negative sign, so this is a reflection, reflection about x. Right, so, and this happens before the upshift. In other words, from the graph of x cubed, that transforms it into the following graph. Okay, so that's what's happening with that negative sign. So let's go ahead and draw the final graph here. So I'm going to the left 1 unit, and I'm going up 1 unit. So here's my center, and it's basically going to be x cubed but flipped like that. Okay, so that's the problem 2a. Let's take a look now at problem 2b. This one has as graph some rational functions. The first one is y equals, and let's see, this is 1 over x minus 1 quantity squared times x plus 2. So notice I can think of this as 1 over x minus 1 squared like that times 1 over x plus 2 to the first power. Okay? If I were to graph each of these individually, this one alone would look like, well, I have an asymptote at negative 2, and it looks like 1 over x, just like that. And this other one has an asymptote at 1, and it looks like the x squared graph. So now I'm going to piece all of that information together, and I'm going to obtain the final graph. So I have, first of all, I have a vertical asymptote at 1. I also have a vertical asymptote at negative 2 from this one. And let's see, let's take a look. I don't have any roots, so it never crosses the axes, because I don't have any zeros in the numerator. As I go off to plus infinity, I approach 0 from the positive side, and then I also have to approach the asymptote. So I have this shape here. Now I know that this came from an x minus 1 to the second power, and as we saw in problem 1, an even power means I stay on the same side of the asymptote, like that. Then I approach the other asymptote here without touching the root. But now, because this comes from an x plus 2 to the first power, I have to flip sides. So that's what's going on here. And you can do a quick reality check, right? As x goes to minus infinity, this term right here is positive. This is going to be negative. So yeah, you do approach 0 from the negative side. Okay, so that's kind of what the graph of this one would look like. Now let's take a look at the other part of problem 2b. So now I'm looking at the graph of y equals, let's see, it is x plus 2 on top over x plus 1 quantity cubed and x minus 3 quantity squared. Okay, I won't break this up into pieces. I'll just go ahead and do it right away. Right, I have
horizontal asymptote at x equals -1 and at x equals 3. So let's go ahead and, I'm sorry, I meant vertical asymptotes. Let's go ahead and draw those vertical asymptotes. Those are the two vertical asymptotes that I have. And I have a 0 at x equals 2. X equals -2, my bad. Just like so. So now let's see. As I go to plus infinity, of course I approach 0, everything is going to be positive. So that on this side of the asymptote, I level off like that, right? This x minus 3 is of degree 2, so I stay on the same side. I don't go down here like the 1 over x function. I have no zeros here, so I have to level up to that asymptote without touching the axes, like that. Somewhere over here there's going to be a min, of course. We're not going to go through that, right? We're just going to give a rough sketch of what this looks like. But this is of degree 3, right? So now this asymptote is a degree 3 asymptote, which means I flip on the other side of the asymptote. And I have to cross that 0, but then as I go to minus infinity, I need to level off like that. And we can check, plug in the negative approach, 0
from the plus side, just like so. So that's kind of what the graph of this function would look like, and then just let me make what's going on with that problem. Okay, let's move on to point 2c.
And what 2c has us do now is it has us also look at two curves. So the first one is y equals the 4th root of 3x squared minus 10. And because this is a 4th root, I have to be careful about the domain of the function. Okay, everything that's under here has to be greater than 0. So I have 3x squared minus 10 has to be greater than or equal to 0, which means 3x squared has to be greater than or equal to 10. And if I divide by 3, x squared has to be greater than or equal to 10 over 3. In other words, the absolute value of x has to be greater than or equal to the square root of 10 over 3. And I'm taking absolute value because really when I take the square root of both sides, I get a plus and a minus. Okay? So that means that the domain of my function is only going to be, let's say this is the positive plus square root of 10/3, and let's say that this is the negative one, right? So I'm only going to sketch the domain for these x values. Everything else is not included in the domain, right? Only these rays going off to infinity. Okay, now let's take a look at this function. Over here I have a square, but then I have a 4th root. As x is large, I can ignore these constants, and I can think of this asymptotically as a 4th root of 3x squared, right? So I ignore the minus 10, and then this is basically asymptotic to a x to the second power, right? If I forget about that 3. I'm sorry, not x to the second power. Square root of x. Okay? And that means what I'm going to do like that.
And I'm going to make it look like the square root of x function. So again, this is just a rough sketch of the graph. And on the other side, I have the mirror image of the same thing. Another way to see that this is the mirror image of this side is simply because I have a square here, right?
which makes this an even function, so it's symmetric about the y-axis. Let's take a look at the other shape. So now I have y equals, and I'm looking at 2 times the cubic root of 2x minus 1 plus 3. So this one is a little bit easier to work with. I don't have any domain problems because I can take the cube root of positive and negative numbers alike. So what I'm going to do is I'm going to rewrite this by factoring out a 2 from under that. So I have 2 times cubic root of 2 times cubic root of, and what I'm left with, x minus a half plus 3. Okay? Which means this is a right shift of a half, and this is an upshift of 3. So let's go ahead and sketch that. This is, let's say this is 1, this is 2, this is a half, and I'm going up 1, 2, 3. And what this is going to look like roughly is simply the cubic root function, like that. A bit
taller like that, right? So that's all that constant multiplying in front does to the function. So that's problem 2c. And lastly, let's go ahead and do 2d. And this one should be fairly simple. First, I'm looking at y is e to the x plus 2 minus 2. So automatically I notice that I have a left shift of 2 units, and I have an downshift of 2 units. And what that looks like is basically like this, right? I have my e to the x base point here. That's what it looks like. I'm moving it to the left 2 units, and I'm moving it down 2 units. So now this is my new base point. The asymptote is going to also move down together with that. So my function looks something like that, right? It's just a shift of the e to the x. Let's go ahead and graph the other one. So now I have y equals ln of quantity x minus 1 plus 1. And what this minus 1 inside by the variable does is shifts it to the right 1 unit, and this one shifts it up 1 unit. So I'll go ahead and I'll draw the baseline graph of ln of x. I'll just draw it dotted so it's not too visible. And now I'm going to move this to the right 1 unit, which means the asymptote moves, so it's going to cross that point now, just like that, and it's leveling off in this direction. So those are the 2 graphs for 2D, and that's it for problem 2, and that's it for the function section of this review packet.